In this video, we're going to talk about more on how to find the horizontal asymptotes of a rational function. So the idea that I want us to carry through this conversation is that horizontal asymptotes describe the eventual behavior. This is really key for a multitude of reasons, and I will tell you what they are in a few seconds. But the idea that horizontal asymptotes describe the eventual behavior of a rational function is possibly the most important idea of all. What does eventual behavior mean? When we're talking about eventual behavior, we're talking about what happens as x grows beyond all bound. So let's look at an example. Okay, so say that we have, 2x squared minus 5x plus 7 over x cubed plus 2. Okay, so I'm not going to talk about all of the different pieces of this rational function. I just want to look at its horizontal asymptote. So the horizontal asymptote is looking at what happens as x grows beyond all bound. So as x goes to infinity, what happens to f of x, or maybe I should say to the value of f of x? What I want you to think about here is the fact that we are looking at values of x that are getting bigger and bigger and bigger. So, in particular, let's look at the numerator. As x grows beyond all bound, what happens to 2x squared minus 5x plus 7? Well, we talked about this on one of our Friday sessions. If x is a very large number, it's really believable that the plus 7 makes virtually no discernible difference, right? Imagine if the value of x is, say, 10,000. Well, x squared, if x is 10,000, is 100 million. Add 7 to that, you don't notice, right? It's relatively speaking, that plus 7 is making very little difference. As it turns out, the bigger x gets, the less that minus 5x plays a role too. So I want to show you this, and we talked about this in one of our Friday sessions. If x is 10,000, 2x squared is 2 times 100 million, so 200 million. It's a pretty big number. Versus 2x squared minus 5x. Well, that's 200 million minus 50,000, right? So that's 199,950,000. Okay? And you can see that this is virtually, like, it's a very small difference, relatively speaking. If we kept going with this and said if x is, say, 100,000, I invite you to make that comparison. So imagine squaring 100,000, right? When you square 100,000, you get 1 with 10 zeros at the end of it, right? That's 10 billion. Imagine having 20 billion of something and then taking away 500,000, right? So like you might imagine this as a question, like imagine somebody who's worth $20 billion, right? and then telling them, hey, like, would you buy this $500,000 condo? That's nothing to them, right? They could buy it in cash. It's a very, very small sum of money relative to what they have. So what you see more and more is the bigger X gets, the less impact that minus 5X has on the 2X squared. And again, this is going to continue being more and more and more the case. So what we're seeing here is as X grows beyond all bound, as X tends to infinity, right, it keeps getting bigger, X. It never stops. So after 100,000, it will eventually get to 1,000,000. After that, it'll eventually get to 10 million, and so on. The bigger X gets, the less and less distinguishable 2X squared minus 5X plus 7 gets from 2X squared. By that exact same token, right, so let's write this in a different color, and this is perhaps even more believable. Let's look at the numerator, at the denominator. Well, as X gets bigger and bigger and bigger, that plus 2 fades into irrelevance very, very quickly. So as X grows beyond all bound, X cubed plus 2, well, that just fades down to X cubed, right? So let's look at both of them, right, together. So as X goes to infinity, f of X goes to, well, we just talked about the denominator and the numerator. As X goes to infinity, 2X squared minus 5X plus 7 goes to 2X squared. And as X goes to infinity, X cubed plus 2 goes to X cubed. So the entire f of X tends to 2X squared over X cubed, which of course the X squared and the X cubed reduce. And so you're left with 2 over X. Now let's think about this together. What happens if you're allowing X to get bigger and bigger and bigger, and then you divide 2 by that? So what happens if you divide 2 by a number, and that number is getting bigger and bigger and bigger? Imagine 2 divided by 10, 2 divided by 100, 2 divided by 1,000. What happens for each of those subsequent increases in the value of X? Say it with me. The value of 2 over X goes to 0 as X grows beyond all bound. So lurking in this little conversation is this really interesting idea of who are the power players when you're looking at horizontal asymptotes. What are you actually looking at when looking at horizontal asymptotes? And as it turns out, the thing that we're really looking at is the highest power, right? The highest power of X in the denominator and in the numerator. So we're going to actually provide, to finish this lesson, a summary that really relies on that highest power that we see in the numerator and the denominator. So I'm going to call this a horizontal asymptote summary using the degree. And I'll say degrees plural because we're going to look at the degree of the denominator and the degree of the numerator. Okay, so quick definition. We're going to call d sub n the degree of the numerator. And we're going to call d sub d the degree of the denominator. So those are just notations I'm introducing to make it easier for us to talk about this. You can use different notations if you prefer them. Okay, so So here goes. If the degree of the numerator is greater than the degree of the denominator, okay, there is no horizontal asymptote. Now, I'm actually going to put a little asterisk at the end of this phrase, and it's an asterisk that I'm going to address in a future video. Yes, if the degree of the numerator is greater than the degree of the denominator, there is no horizontal asymptote, meaning the graph will not stabilize down to a particular constant, but that doesn't mean there is no asymptote. That does not mean that there's no like interesting thing to look at. It's just something that we don't look at a ton. We look at it a little bit, and we'll look at it in a future video. If the degree of the numerator is smaller than the degree of the denominator, the horizontal asymptote is the x-axis, also known as the line y equals 0. And then last but not least, if the degree of the numerator is equal to the degree of the denominator, and I'll do a quick example with you on that in a second, the horizontal asymptote comes from the ratio of the leading coefficients. So for example, if your function is something like 3x minus 2 over x plus 5, okay, the degree of the numerator is equal to the degree of the denominator, and they're both equal to 1, right? The numerator and the denominator are both linear. Well, our leading coefficients, if we wanted to write the denominator with a coefficient, we would write it as 1x plus 5. So our leading coefficients are 3 and 1. So for our horizontal asymptote, we look at the ratio of the leading coefficients, and we would say that the horizontal asymptote is the line y equals to 3 over 1, which is just 3. Okay? Now, I'm not going to talk about this in this lesson, but I do want to touch on one last piece before we stop. Remember, the horizontal asymptote is the eventual behavior of a rational function. So we start to see the appearance of the horizontal asymptote for larger values of x. Sometimes you see it very quickly, even for values like 5 or 10, you're already beginning to see that the function's going to stabilize down to it. Sometimes it may take longer, but the point is that the horizontal asymptote really only describes what happens down the line. It is not there for every single value of x. The function does not like hover around it for every single value. What this means is that it is possible for a rational function to cross its horizontal asymptote, sometimes even more than once. On that note, we'll end this video here, and in the next lesson, we'll look at an example graphing a rational function where we actually talk about where or how the graph might cross the horizontal asymptote. See you next time.